Okay, welcome to this another video lecture on basic surveying. Now today we are in module 9, and in module 9 we will be covering computation and adjustment. First we will start with lecture number 1. This is our entire schedule of all the lectures. Now in lecture number 1, what all we will be covering? We will be covering the concept of error, of adjustment, methods of adjustments. We will see that we need a mathematical model for the adjustment, and a little bit about least square adjustment. We will see all these with examples. Well, let us start with the very basic question. The question is, why do we need the adjustment? Okay, in surveying, whenever we are taking the observations in the field, what happens? As we have seen, in taking observations, whatever we are measuring, we always make use of some instrument. Then a person is involved. Then there are various kinds of conditions because of the climate, weather, okay, atmosphere. Now the end result of all these is we want to measure, for example, a distance because of the limitations of the instrument, chain, tape, or EDMI, because of the limitations of the observer, or because of the problems in the weather. Okay, there is some weather is not very good, or maybe for the kinds of the ranges for which, or temperature range for which the chain has been designed, the weather is not like that, or the temperature there in the field is more. So what happens? The end result of all these is our measurements will have some error. We have seen this. Now the errors, as we can see here in this slide, errors can be, we define in 3 categories. Number 1, blunders, those which can be detected by some statistical method. Okay, blunders means they are very far away from the main group of values or observations. We can scan the observations, we can find, no, there is something wrong with this particular observation, so that's a blunder. There are methods of detecting those, eliminating those. Then the other kind of error, we know about that, that is a systematic error. Means for that error, we can write a physical model. We know the reason why this error is there. By taking the measurements, for example, the temperature measurement in the field, and we know the temperature at which my tape has been designed. By finding the difference of these two, what we can do, we can apply a correction for the expansion of the tape because of the temperature difference. So what we are doing, we are writing a mathematical model here, or physical model. Using this physical model, we can eliminate the error. So all those errors about which we know their source and can be eliminated easily, we see them systematic errors because we can eliminate those. Well, from the observation, the blunders have been eliminated, the systematic error has been eliminated, but still there are errors in the observations. We know this, we have already discussed. Still our observations are not the true values. True values means the distance between 2 points. What is their exact distance, the true distance? We are not able to measure it because still there are many sources of errors about which we do not know. Those errors which we cannot model, which we say accidental errors or the random errors. So, as we can see here, we don't make the observations which are true values, rather our observations will have the errors. The errors are of these categories. Now, we have seen that random error will remain in the observation even if we can eliminate blunders and systematic error. So what? The observations, this is very important here. The observations, because of the error present in the observations, fail to satisfy geometric and observation conditions. Now let's look at that. What is the meaning of this? We'll talk about these one by one. Let us first talk about the geometric condition. What is the meaning of geometric condition? Well, here in the slide, you will see there are 3 points A, B, and C. Now these 3 points A, B, C are physically there in the ground. Okay, you can locate 3 points in the ground. What we are doing, we are measuring the angles which are forming this triangle ABC. Okay, so as you can see, the angles theta 1, theta 2 and theta 3 have been observed in the field. Alright, now the meaning of geometric condition is, because there are 3 points in the field, they form a triangle, and we know the sum of internal angles of the triangle. If we say theta 1 plus theta 2 plus theta 3, this should be 180 degrees. This is the geometric condition because there are 3 points on the ground forming a triangle. But do our observations satisfy this? If theta 1, theta 2 and theta 3 are our observations, this will not be equal to 180. As you can see here, this will not be equal to 180. Why it will not be equal to 180? Because in theta 1 there is some error, in theta 2 there is some error, in theta 3 there is some error. Let us say V1, V2 and V3. So because of that, our observations are not satisfying the geometric condition now. There may be many more geometric conditions depending what kind of figure we are talking about. If we have a polygon, okay, we can also define a geometric condition for the polygon. Similarly, many more. These conditions are formed because of the angles, because of the lines also sometimes. Well, the next condition is the observation condition. Now, as you see over here, we have a point O. At that point, we are measuring the angles alpha 1, which is between point C and B, and alpha 2, which is between point B and A, as well as we have also taken one more observation, that is alpha 3. So alpha 3 is observed in the field between C and A. Now just think of the case of theodolite. What do we do in the theodolite? We'll take the theodolite, we'll set the theodolite at point O. Okay, it should be exactly above point O. The vertical axis of the theodolite, it should pass exactly over the point O. Will it be so? No. There are problems in centering. We cannot center truly. Well, there is some error. We need to keep some ranging rods at A, B and C. If we keep the ranging rods there at A, B and C, can we keep the ranging rod exactly above A, B and C? No. Well, now we are taking the observations. We need to bisect. Can we bisect exactly the center of the ranging rod? No. Again, there are problems. You know, the problem could be when we are reading the observations. If you see here, we are trying to read somewhere here. Well, what is the reading? Can we read exactly? No. So what is happening? In this process, there are many sources of errors, and those which we cannot model, source of random errors. Now, if that is the case, what will happen? Alpha 1 will have some error, let us say V1. Similarly, alpha 2 will have V2 and alpha 3 also will have V3. The observation condition means had these been true values, no errors at all in taking the observations, then alpha 3 should have been equal to alpha 1 plus alpha 2. Yes, if they are true values, but no, we are not observing the true values. So, no more alpha 3 is equal to alpha 1 plus alpha 2. So, this is the observation condition. So, what we said? We said, well, our observations should satisfy the geometric condition and the observation conditions. Well, now the important thing. We have seen the geometric condition and observation condition. Also, we have seen the observations which you are taking in the field do not satisfy these conditions. But that is not desirable. You know, we have a triangle there in the field, and for this triangle we observe these 3 angles, and now we find that sigma of these angles is not equal to 180. Can we live with that? No, we can't go further with that, because there in the field we are observing a physical quantity, the shape of the triangle, isn't it? The sum of three angles has to be 180, but our observation do not say so. What should we do? Now here comes the concept of adjustment. We need to alter our observations, change our observations in such a way that they start satisfying this particular model or the condition. Okay, we'll see how we do that later on. But right now we will see some definitions. One is observation and the second is the desired quantity. What these are? Observation means, if, let's say first talk about the desired quantity. Desired quantity is, we want to measure this full length L, but we have a tape which is smaller in length than this full length capital L. So with that we are observing this in parts. We are observing first L1, then L2, then L3. So our observations are L1, L2 and L3, and the desired quantity is L. Similarly here, let us say we want to, our desired quantities in this case are alpha 1 and alpha 2, but we have also observed alpha 3. So desired are alpha 1 and alpha 2, but in the case of the observations, our observations are alpha 1, alpha 2 and alpha 3, because we can find the values of alpha 1 and alpha 2 which are desired by these three observations. Okay, so what we are doing here in this case, we are introducing a redundancy in the observations. All right, so right now we should understand the difference in observations and the desired quantity. Well, next, as we have seen earlier also, and as I was talking, our observations should satisfy a model. Okay, the model in this case was sigma theta is 180. That's the model. Observations are theta 1, theta 2 and theta 3, and sigma theta should be 180. So what we are trying to do, we are trying to alter our observations, correct them, apply some corrections to the observations in such a way that the estimates. So what we are doing in observation, if theta 1 is observation, I am applying a particular correction to this so that I get theta 1 hat. So theta 1 hat is the estimate. What is the meaning of this? In observation we applied the correction by some method, we get an estimate. So this estimate now should satisfy our model. That means sigma theta hat should become 180 because we have applied the corrections. Now this process is called the adjustment. So for the adjustment we need that model, and our estimates should start satisfying that model now. Now again, some more things. The model which we take or which we make use of in adjustment are of two types. One is functional model, the second is stochastic. Now what is the difference between these two? What these are? This is very important. Before the adjustment, we need to define this model. We need to be very, very clear about the model. The model which our observations should satisfy or estimates should satisfy. We need to know about that model. The functional model is, as we have seen earlier also, sigma theta is 180. It's a functional model. Similarly, alpha 1, alpha 2 is equal to alpha 3, whether by the geometric condition or the observation condition. As we have seen previously also, these are the functional models which are because of physical or geometric conditions. Now the stochastic model is, so far in our functional model, we did not talk about the quality of the observations. Okay, someone who was capturing theta 1, this gentleman, let's say his name is A, and the gentleman who is capturing theta 2 is B. The gentleman A is very sincere than the gentleman B, and then they come out to me with two sets of observations, one for theta 1, one for theta 2. If I know about these two gentlemen, or maybe let us say A was working with a very precise instrument while the B was working with a non-precise instrument. In that case, what can I do? I can differentiate now in theta 1 and theta 2. I can say theta 1 observations are better, are more precise. Theta 2 are not. I can give weights. Okay, theta 1 observations have higher weight, while theta 2 observations need to be given less weight. So in my functional model, when I am putting this data, I need to also take into account the quality of the observations. So the way we take the quality of the observations into account, we say that as stochastic model. So we need to define that model also, okay, about the quality of the observations. Okay, now we'll take one example here. Now in this example, as you can see, A, B and C, they are 3 points, okay, point A, point B and point C, they are on the ground. What we are doing, A is the benchmark, okay, and the elevation of A is known, it is capital E. Using this benchmark, we want to determine the elevation of B and C. This A point is known, is the benchmark. So what do? We know the process. We carry out, starting from A, we will carry out the leveling, it could be the fly leveling, up to B. So we know the difference in elevation between these 2 points. If I know the difference in elevation between A and B, I know the elevation of RL, we say, RL of A, I can find the RL of B. Similarly, starting from B, I can go to C, and then again I can find the difference between point B and the C, their RL difference. I add it to the RL of B, I can find the RL of C. Okay, one more procedure is possible. This way we can determine these two, B and C, their RLs. One more way is possible. I can straight away, I go from A to B as well as I go from A to C. So what we are seeing here, we are doing the same thing. We have done this over here. From A, we found L1. L1 is the difference between RL of A and C. Using that, we can find the value of X1. X1 is RL of C. Now, from X1, I went to B. Okay, the difference in RL between C and B is L2. Now, using this route, I can determine the RL of B also. But what we did, again from B, we went back to A. So now the RL of B can also be determined directly by taking into account this L3. Okay, it's a very simple thing. Now here, as per our adjustment, X1 and X2 are the desired quantities. What is the meaning of that? We want to determine the RL of B, which is X2, and the RL of C, which is X1. These are the desired quantities. We know E. E is RL of A. That means RL of A. Well, the observations are L1, L2 and L3. Because what all observations we have done here? We have observed the difference in RLs, L1 here, L2 here and L3 here. Okay. So what we want to do? We want to determine X1 and X2 now. So what we will need? We'll need a model now in order to determine this. So what model we can make use of? A model is required. We can write this model in order to determine this desired from the observed quantities and the known. The model could be, I can determine X1 as E plus L1. What you can do, you can go back to the main figure. For example, x1 is E plus L1. Okay, this is what I am writing now. X1 is E plus L1. Next, x2 is E minus L3. I want to determine x2, which I am writing as x2 is E minus L3. Minus because this we have done the survey this way, B to A, and this we are writing as positive. Okay, so we have to just take into account the sign. That's why I am writing minus here. So x2 can be determined this way also. So x1 and x2 both are known, E plus L1 and E minus L3. Alright. So what it will do, it will give me one unique solution. But at the same time, what we observed, we can also find, also x2 by E plus L1, that is RL of, that is x1 plus L2. Now what is this? x2 can be also determined as E plus L1 plus this observation here, L2. Alright, one more way of determining the x2. Now we have a model now, and this is the model which defines this entire set of observations, and using this model we can determine x1 and x2. But there will be some questions now. What are the questions? One more thing which is important here. We have so far come out with these three systems within our model. Is there any other possible? For example, I can write one as L1 plus L2 plus L3. Obviously, you can make a guess now that this will be equal to 0. Because why L1 plus L2 plus L3 will be 0? We started from this point. The difference of L1 is difference between these 2 points, A and B. Okay, then L2, then L3. So what we are doing, we are starting from a point, again coming back to the same point. So if we sum up all these, wherever we go, we have seen this in our loop concept also when we are talking the labeling. L1 plus L2 plus L3, that should be equal to 0. But this model or this system is not independent. The meaning is I can derive it from these three equations. So it's not independent. We are looking for systems which are totally independent. Over here, all these three are independent. Well, after forming this model, what we want to do, we want to determine x1 and x2. How can we determine that? In order to determine that, what we can do, we can make use of equation 1 and 2. Over here, I am talking about these equations, equation 1 and equation 2. And by solving these two, I can find x1 and x2. That's very easy. But at the same time, I can also do it for, by taking equation 2 and 3. Also I can do it by taking 1 and 3. So what we are saying here, the solution for x1 and x2 can be found by these three roots. Now the problem is, which out of these three? Because this first set will give one value of x1 and x2. Similarly, the second set will give one value of x1 and x2, and the third one also over here, that will also give one value of x1 and x2. Now the question is, out of these three possible solutions for x1 and x2, which one should we take? Okay, why this problem is coming here? This problem is coming here because we have redundant observations. What is the meaning of redundant observations? We have seen this before, but let's talk about it once again. In this triangle is theta 1, theta 2, and now the triangle is defined. I can find this value of theta 3 as 180 minus theta 1 plus theta 2. So this gives a unique solution. There is no redundancy here. But the problem with this is, if theta 2 has some error, okay, very large error. Errors are always there, but a very large error is there. This large error will also creep in theta 3. We don't have any method of checking that. Okay, but if we are also observing theta 3 now, we are observing it. So if there is a very large error in theta 2, theta 1 plus theta 2 plus theta 3, this will not be equal to 180, as well as it will be very much away from 180, because in theta 2 there is a large error. So by this redundancy, what we are able to say, we are able to check for the errors. So redundancy is always to help us. So same is the concept here now. To solve for this problem, a problem with the model here, what the problem was, x1 and x2 can be determined by 3 rows. Which one is better? It's not a problem really. Rather, we need to find a way to solve for that. It's not a problem. The way to find an answer in these cases is through adjustment. Okay, we want redundancy in the observations because it helps us to look for the errors. Number one, in case of redundant observations, we need to have a way so that we can find a solution, the solution which is consistent with the functional model, which the observations should satisfy. Okay, that we can do through the process of adjustment. So over here, the definition is a procedure. What is the adjustment? Adjustment is a procedure to obtain desired quantities. Our final aim is to obtain desired quantities, not the observations, okay, which are consistent with the applicable models, is called adjustment. Okay, that is important. Now how do we do that? How do we carry out the adjustment? What should we go, how should we go about? We'll see one approximate method for that in order to understand the process. Then we'll go for other method. This is an approximate method here. And in this method of adjustment, let us say we are talking about our previous problem only, when we had taken the differences in elevation between A, B and C, L1, L2 and L3. Our case was like that. And we know that in that particular problem, where it is L1, L2 and L3, L stands for difference in levels. Okay, so in this problem we know that L1 plus L2 plus L3, this should be equal to 0 if the observations do not have any error. But due to error in L1, L2 and L3, it will not be so. We also understand this because our observations, whatever the precision we are applying in the field, still the random errors will be there. Yes, they will be less, amount will be less, but they will be there. Okay, so let us say if for L1, L2 and L3, the true values are L1T, L2T and L3T, these are the true values. Had there been no error at all, in that case this model will be satisfied, because true values means there is no error. But do we observe true values? We cannot. What we observe is with some error. So observations are with some error. Okay, one more important concept we are going to talk here. Our observations are with some error, not the true values. Now from our observations, we try to reach true values, or rather we say we try to reach the most probable values. Okay, those values which should satisfy the model. So what we are trying to do? We are trying to reach from the observations an estimate, L hat, as we had seen before also. An estimate, so that our estimates are the best under the condition of the model. The adjustment should give us the best possible solution, okay, of the estimates. There should not be any other solution which is better than that. That's the desired goal, desired aim which we want to achieve by our process of adjustment. Now, this is why, so what we are writing here, our estimates, if we, because we denote the estimates by hat, so L1 hat, L2 hat and L3 hat, these are the estimates. So finally, our estimates also should satisfy this L1 hat, L2 hat and L3 hat. The sum of these should be equal to 0. Okay, because our desire is that they should satisfy the functional model. Now, we write L hat as L plus V. Here L is the observation, we know about it, something which we are measuring in the field, observation, and V we say as residual. Okay, so in observation, if we add the residual, we get the estimate. Now using this, what we can do, using this particular L hat is L plus V and the equation 4, we can write L1 plus V1 plus L2 plus V2 plus L3 plus V3, it should be equal to 0. Okay, now we can further write V1 plus V2 plus V3 should be equal to, I am taking all these observations on the right hand side, should be equal to minus L1 plus L2 plus L3. Let us say this minus L1 plus L2 plus L3 is equal to minus E. Now in this case, where is the functional model? The functional model is this, isn't it? The functional model in this particular problem is, let me describe that problem again, L1, L2, L3. So our functional model is L1 plus L2 plus L3, it should be equal to 0. That's the functional model. Now what is the stochastic model in this case? Stochastic model will talk about the quality of L1, L2 and L3. If L1, L2 and L3 all are observed with same precision, we'll say, well, all of them have the same weight. If L1, L2 and L3 are observed with different precisions, we can say these observations have different weights, isn't it? So that's the stochastic model. So stochastic model means, do we know about the statistical property of observations of residuals? Okay, now in this case, two cases as we have seen. If all the observations have been taken with same precision or not, okay, the question is, were all observations taken with same precision? Well, there could be two answers, yes and no. If the answer is yes, all the observations were taken with same precision, okay, then we can say the residual in all the observations will be same. Now why we are saying this? There in the field we are observing L1, L2 and L3. Now we conclude that L1, L2 and L3 have been observed with same precision. Means whatever is the error in L1, same is the error in L2 and L3. Okay, that's the assumption here. If it is so, that's why we are writing that V1 and V2 and V3 should be equal to, let us say, V. So we can write now, because earlier we were writing as V1 plus V2 plus V3 that was minus E. So we can write this as now 3V is equal to minus E. So we get the value of residual as minus E by 3. Now with this, what we can do, if we know the value of residual, I can apply it on the observation L. This V is being applied to get the estimate. So the estimates will now satisfy my functional model. So what we have seen in this example? In this example, we saw a method of adjustment. We had these three, L1, L2 and L3. Okay, we made an assumption that L1, L2 and L3 have been observed with same precision. So the error is same. We found the total error because L1 plus L2 plus L3 is should equal to 0, but it was not. Whatever is the total residual, we say that is the total error. Now this total error is being divided in L1, L2 and L3. So accordingly we are applying the correction, isn't it? So by finding the correction, by applying the corrections in L1 and L2 and L3, we are finding the estimates L1 hat, L2 hat and L3 hat. And that way this L1 hat, L2 hat and L3 hat, these three will satisfy our functional model, obviously. Well, here the case was, if the observations are taken with same precision. If it is not so, if the observations are not taken with the same precision, okay, now what could be the case? The case could be when these were observed, L1, L2 and L3. When these three were observed in the field, over here, let's say this is a very large length, 10 kilometer length, while it is only 5 kilometer and it is 7 kilometer. If you recall, in our labeling exercise, we were giving precision to the labels, depending how many number of settings of the instrument were there, also by the length of the label net. So what we can do here, we can assign the weights W1, W2, W3 as per the length. For the length is 1 by 10 kilometer. Okay, let's wait here. 1 by 5 kilometer and 1 by 7 kilometer. So what we are doing, more the length, less is the weight. Of course, there is a special way of doing this, which we have discussed in labeling. But here we want to see it, yes, individual observations can be given the weights, as in this case. Now, if these individual observations are of different weights, what to do? How to apply the corrections? How to adjust the observations in this simple case? So we know that V1 will not be equal to V2, will not be equal to V3. The residuals, the corrections will not be same. Okay? Now, if they are not same, in addition to the equation V1 plus V2 plus V3 that was equal to minus E that we have seen, we will also have to use this equation. So now we are using these two to find the solution. Over here we see V1, V2 and V3 are having the values which are related with their weights of the observations. So what we have seen in this case, that we are adjusting the observations, we are finding the L1 hat, L2 hat and L3 hat, the estimates, and these estimates, they satisfy the functional model. At the same time, we also took into account the stochastic model. We took into account the quality of the observations, if the observations were of same quality or different quality. So we started giving the weights. There are methods that how we can apply the weights. Okay. Now next, we go for the concept of least square adjustment. What we will do today, we will try to understand it, the least square adjustment, and then later on we will get deeper into it, because we will be mostly making use of this method of adjustment. We do not go by this approximate method. But in the previous example, where we have seen this approximate method, Actually, if you find the solution for that problem by least square, the answer will be same. Let's say, well, what is the least square adjustment? Over here, I'm giving you just a concept. Let us say this is time of travel t, and this is the distance s. Now, how s is related with t as s is v into t, where v is a uniform velocity. Okay, there is a uniform velocity, no acceleration, and these are related like this. S is v into t. Now, there in the field, we have a stopwatch, and we are seeing something moving with the uniform velocity. And what we are doing, we are observing the time and the distance. Okay, we are observing how much it has moved, all right, and we are observing the time, at what time we are taking that observation. So, in the stopwatch, I say, okay, time is 1 second, it has moved by certain distance. Time is 2 seconds, it has moved by certain distance, 3 seconds and 4 seconds. Now, in this process, where are the sources of errors? The sources of errors are in observation of the time, because I am taking the time, isn't it? Also, the source of error is in observing the distance, how much it has moved. I am saying it has moved 10 centimeter. But am I really able to observe that well? Isn't it? So, there are sources of errors here. And these are, we are considering as the random sources of error. If in this process, I take only 2 points, I observe a point here, at this time it has moved this distance, at this time it has moved this much distance. So, what we will have only 2 points here. Now, using these 2 points, if I want to find v, the velocity, what I will do, I will simply join these 2 points, isn't it? And the slope of this line is known. So, this is also a problem of line fitting. Okay, we always do it. If we have 2 points and I need to fit a line to these, I can fit a unique line. Okay, I have a unique solution. Now, in this case, for this v, I have a unique value. Let's say 10 meter per second. That's the unique value. I don't know any other value of v because it's a unique solution. I made the observations only at 2 points. Okay, so if we have 2 points over here, I can always fit a line through these, and it's a unique line. Next, if we have now more number of points. More number of points means we are taking the observations here at this instance. T1 is S1 distance, T2 S2 distance, T3 S3 distance. If it is so, our first point, our second point, and our third point, I have displaced these points farther here so that we can understand the process. Otherwise, this point should be also somewhere here. There is some error, so it will be displaced a little bit. I have displaced this more. Well, if this is the case, and we have to fit a line, what I can do, I can fit a line through these 2 points. So that gives me one value of the velocity. I can fit a line through 1 and 2. It will give me the second value of the velocity. I can also fit a line through 2 and 3 points. It will give me a third value. So the same question which we were talking earlier, out of these 3, V1, V2 and V3, which one is more correct? How to take a decision here? Isn't it? I can have the 3 values. I have the 3 lines fitted to these points. Which one is more correct value? We can't say anything about that. Which one? Is this V1, V2 or V3? Similarly, over here we had only 3 points. We can also have a situation where we have a large number of points. Okay, I can have one line, another line, another line, another line, all values of the velocity. So V1 to Vn, which one is the more correct one? So in these problems, what we try to do, we try to find a solution which satisfies our model, which is the best possible solution in this condition. Okay. Now the meaning of best possible solution, that is what I am going to give you. Fine. What we do, we try to fit a line here. Okay, let us say we fit a line which is like this, and we say this value V is the most representative value. What is the meaning of that? The meaning is, if we fit this line to these 3 points, there are deviations of the line, okay, from these points. So these deviations I can say as, let's say V1. Okay, over here V1 stands for residual or the deviation, V2 not for the velocity, and V3. Now we will go for a line, as over here I have seen the line by red color. I am saying this line is the best line which can be fitted in these 3 points. We will say this line to be the best line only if, when we will say it best? We will say it best only if this line deviates, because it is deviating from point number 1, point number 2, point number 3. Its deviation is such that overall deviation of this line from all the points is least, is minimum, isn't it? I can have a line over here, for example this, but this is not the best solution. So what we are looking for, our fitted solution, the value of the V which we are finding, the line which we are fitting, should be such that its deviation from our observations should be least. All the observations taken together. Now how to realize that? These deviations are, some are negative and some are positive, isn't it? So we want to take all the deviations into account. So the way we try to achieve it is, we say that sum of square of all the residuals, all the deviations should be minimum. So as we have seen in this problem, similarly, as we are talking of the other problem, if we have several points here, the line which will fit among these, let us say this is the line which is the best. The meaning is sum of square of all these residuals. These residuals, let us say we say as V, so sigma V square should be minimum. And if we are able to find this line, we say this is the line which we are fitting over these points by method of least square. Okay, the least square that is being communicated by this sigma V square and this minimum thing here. So the same thing we will try to do in our observations also. In our observations mean, as we are talking of the case of a triangle, we are observing there theta 1, theta 2, theta 3, and our functional model was sigma theta should be equal to 180, isn't it? So what we try to do, we try to apply, we first know somehow the weights of these observations. Okay, these are the weights. Then as per the weights, we find corresponding to each observation the residual V1, V2. These are the residuals. So these residuals should be such that V1 square, if I write it this way, V1 square plus V2 square plus V3 square, this should be minimum. Only for if my solution, if my V1, V2 and V3 are coming from the proper method of adjustment, then in that case one and unique solution will satisfy this. For any other solution, this sum of square of residuals will not be minimum. Okay, so in our method of adjustment, we'll try to realize that what we are doing, we are trying to change the values of theta 1, theta 2 and theta 3, the observations in the field, in such a way, alter them in such a way that they start satisfying our functional model, as well as the changes which we have applied to them by means of these residuals are such that we reach the best solution in the least square sense. So what we have discussed today, we talked about the concept of adjustment. Why we need the adjustment? Because they are errors. We can eliminate blunders, systematic errors, but random errors are still there. We also say them accidental errors, cannot be eliminated. But if our observations have the random errors, they will not satisfy our functional model. We cannot go with observations which have errors. We need to adjust them. In order to adjust it, we have to take into account the functional model which the observations should satisfy, as well as we need a method which should give us the best solution. So that we saw today is the least square method. Thank you.